So we're going to cover 4 different types of questions regarding differentials and linearizations. So the first one is finding the differential. So when you find the differential, it's basically finding dy. Well, we know that when we have dy over dx is equal to something, if we just multiply both sides by dx, we get that something times dx, and that's our differential. So let's do that. So let's take the derivative of this. We get dy over dx is equal to, and then this seems that we're going to have quotient rule. And since this is secant squared, we're also going to have product rule, or not product rule, but chain rule on the top. So we have 2 secant x, because that's our outside, times the derivative of the inside, which is secant x tangent x, and then times the bottom, which is x squared plus 1, minus the derivative of the bottom, which gives us 2x times the top, which is secant squared x. And that's all over the bottom squared, which is x squared plus 1 squared. So if we move dx onto this side, that's our differential. But we can also make this look nicer by just factoring out a secant, 2 secant squared on both sides over here. On the top, we factor 2 secant squared x on the top. This will make it look nicer by having x squared tangent x plus tangent x, all right? Because we had, basically, we pulled out this part right here. So we have tangent x times x squared, tangent of x times 1. And then we pulled out this 2 and this secant squared. So all that's left here is a negative x. And that's all over x squared plus 1 squared. So that's the first part, which is how to find a differential. So the second part is going to be an approximation. So if we see approximation of something, we have to find what our x is to start off, what our y is, and then what is our delta x, which is also going to be equal to dx. And then we need to find our differential, which is dy. So let's do all of that just now. So if we have f of 3.1, let's say fx equals to 3. So if we plug in 3 here, we have the square root of 3 squared, which is 9, minus 5. This gives us the square root of 4, which is equal to 2. So that's a really nice number and easy to calculate, so let's stick with that. Then for y, we just calculated it, is that at x equals 3, y equals 2. Delta x, so the difference between 3.1 and 3, or you can just say 3.1 minus 3, this gives you 0.1, and this is a positive. So delta x is positive 0.1, and this is also equal to dx, and dy is going to be our differential. So if we take the derivative of this and then multiply by dx on both sides, we have dy is equal to, then the derivative of this, and if we just look at this, this is just basically all that to the 1/2. It's the same thing. So we say 1/2 x squared minus 5 to the negative 1/2 times the derivative of the inside, which is 2x, and this will give us, so the 2's cancel out, and we get x over, and then the square root of x squared minus 5 times dx. Because look right here, we did not put a dx here because we wanted to put it on this side. So let's compute dy. This will give us, if we plug in, we have 2 over, and then like we said, when we have x equals 3, or not 2, rather 3, over square root of 3 squared minus 5, so we have 9 minus 5, and like we said, that is equal to square root of 4, which is 2, times dx, which is 0.1, and that will give us 3 over 20. So that's our change in y, or our approximated change in y. It's not exactly it. So if we calculate our new y, essentially, f of 3.1 will equal our old y plus our change, which will be 2, which is our old y. So that's basically like f of 3, and then plus 320, 3/20ths. So this is basically our dy. And that will give us 43 over 20, which is equal to 2.15. So this f of 3.1 is approximately all of this. Now we have our third type of problem, which is a linearization. So if we find the linearization of something, all it's asking is just to put it into a regular line. So I don't like the word linearization. All this means is just we're finding a y equals mx plus b line of the tangent. So if we find a tangent, we know it's a line, and so we can put it into this form. So I'm going to use my y minus y1 equal to m times x minus x1 point slope formula. This makes life really easy. So if I have y at equals 4x squared equals at x equals 1, let's figure out what my y and my x is. So y is equal to 4, and then 1 squared, like we have here, which equals to 4. So we know that x equals 1, y equals 4, and then what we'll have to do is just find our m, which is our slope. Well, dy dx is our slope at any point on the function. And if we take the derivative of this, we get 8x. So when you plug in x equals 1, which gives us the slope at x equals 1, y equals 4, this gives us 8. So if we just plug into our equation here, we get y minus 4 equals 8, which is our slope, times x minus 1, which is x equals 1. And you can simplify this even more if you wanted to equal y equals 8x minus 4. We had 8 times negative 1, which is negative 8, and then we added 4 to this side to get this. So that's the linearization at x equals 1. And then the last type of problem we can get is a propagated error and a percent error. So in order to solve this, we have to have a couple things. One, for percentage error, we're going to have to know what our actual area is based on the square. And then we need to know what our dx is, which is our uncertainty. And then we need to know what our x is. And we're basically just figuring out all these elements. So let's go by this step by step. So we have a side of a square, and we know that a square has 4 equal sides, right? So this is 10, so this is 10, also 10. And we have an uncertainty of 1 over 32 on the length of this side. So if we want to find the propagated error in the area, we're basically trying to find the differential of the area. That's about it. So if we have area is equal to, and we know it's one side times the next side, so if we call these x, we can just say a equals x squared. So we have dA is equal to 2x and then dx, right? So do we know our x? Yeah, we said x equals 10. Do we know our dx, which is a little tiny change? Well, yeah, we know our uncertainty is 1 over 32. That's basically a little tiny change in our measurement. So we can say this is equal to 2 times 10 times 1 over 32, which gives you 5 over 8, and we say plus or minus. Because remember, we could either record this as 1 over 32 more than what it actually was, or less. Now that we have our uncertainty, we can basically, that's our propagated error, right, in our area. We can have plus or minus that much in our area. So that's basically number 1. For number 2, which is the approximate percentage error, which is also called the relative error, those both mean the same thing. We just have to divide this number, which is our propagated error, over our entire area. So you know that area is equal to x squared, which is 10 squared, which gives us 100. So our percentage error, or our relative error, is basically dA over A. How much of our propagated error over our entire area actually matters? So we have 5/8 divided by our 100, right? So this gives us basically 5 over 800, which is equal to 0.00625. So if we wanted to make this in percentage, we just multiply by 100%, and this gives us 0.625% error. So that's our second part, which is approximate error. So we just covered 4 different examples of differential questions.